In this video, we're going to be looking at several examples involving sequence convergence, as well as a few more useful theorems to help us determine whether a sequence converges or diverges. So in these first couple of examples, I'm interested in determining if the sequence converges or diverges, and if it converges, finding the value the sequence converges to. I have my first sequence as having the nth term be 3 plus 5n squared over n plus n squared. So remember, the definition of sequence convergence involved looking at the limit as n goes to infinity of that nth term of 3 plus 5n squared all over n plus n squared. Okay, so we want to think about the techniques that we used for limits and infinity back with functions. When I had just powers before of powers of x over powers of x, I would divide by the highest power in the denominator. So that's what we're going to do here. So the highest power in our denominator is n squared, so we can divide each of these numerators and denominators here by n squared. So I'll have 3 plus 5n squared divided by n squared and n plus n squared divided by n squared. So this gives me 3 over n squared plus 5 all over 1 over n plus 1. Okay, and then note that just like we had the limit as x goes to infinity of 1 over x to a power was 0, we have the limit as n goes to infinity of 1 over n to some power r is going to be 0 as long as that power is positive. Okay, so 1 over this really big positive number raised to a positive power is going to be getting smaller and smaller and smaller. So we can see that this 3 over n squared here is going to go to 0, this 1 over n is going to go to 0, so this limit will be equal to 5 over 1 or 5. So we can say that the sequence in this example, our sequence here an, we can just write shorthand an curly braces here, converges to 5. Okay. Notice that the 5 that we got here could also have been found with the shortcut by noticing that I have the same highest degree of n in the numerator as the denominator. So my highest power in the numerator was n squared, my highest power in the denominator is n squared. So when that happens, this algebra of dividing by the highest power in the denominator will end up giving you that the limit is just the coefficients of those highest power terms. So it would be 5, which is the coefficient of my n squared, over 1, which is the coefficient of n squared here in the denominator. Okay, so you can use that shortcut as well in other problems. All right, so let's look at one more example of this type. So I've got an equals n cubed over n plus 1. So I need to look at the limit as n goes to infinity of n cubed over n plus 1. Okay. Notice that the highest power in my denominator here is n, so I'm going to divide both the numerators and denominators here by n. So I'm going to have the limit as n goes to infinity of n squared over 1 plus 1 over n. So notice that this 1 over n part is going to go to 0. So I'm going to have the limit as n goes to infinity of n squared over 1 essentially here. So this will be equal to infinity. Okay. So here we can say that our sequence, since I didn't get a finite number for the answer, the sequence an in this case diverges. Okay. So before we get to some more examples, we need to mention a few more, theorems that are going to be helpful for solving more involved, answering more involved questions about sequence convergence. So the first useful theorem that we have is the squeeze theorem. So remember, we had a squeeze theorem for limits of functions, but now we also have a squeeze theorem for our limits of sequences. So our squeeze theorem says that if an is less than or equal to bn is less than or equal to cn for all n bigger than or equal to some big N, this is just saying that this inequality holds far out in the sequence maybe. After some point in the sequence, we'll have the nth terms of these three sequences satisfy this inequality. Okay, so if we had that inequality and the limit as n goes to infinity, as n goes to infinity of an equals the limit as n goes to infinity of Cn equals some number L, then the limit of that inside sequence Bn also has to be going to L. Okay, so the picture that we have in mind is that Bn is between this sequence An. Let's pretend An looks like this. Cn maybe looks like this. Okay, and then Bn is between these after some point. Okay, so it has to be going to the same limit value as the An and the Cn. Okay, so we'll see that's going to be useful in some different examples that we'll look at. Another really useful theorem has to do with when a sequence is composed with some other function. So this theorem says that if the limit as n goes to infinity of an is equal to L, and we have a function f that's continuous at L, okay, then what can we say here? Well, we can say that the limit as n goes to infinity of f of an will be equal to f of L. Okay, so we had a similar result when we were dealing with compositions of functions where an was some maybe g of x. This is saying that if your function will be continuous at what the limit as n goes to infinity of an is, if f is defined at the limit as n goes to infinity of an, then you can pull that limit inside and look at the limit going to f composed with that value. Okay, so the idea is that we would be looking at f of the limit as n goes to infinity of an. Okay, so we can pull that limit notation inside as long as our function is going to be defined at what that number comes out to be. Okay, so we have one other result that will be useful here. This has to do with cases where you have something that has maybe alternating sign or negative signs in the sequence itself. So this says that we can look at the absolute value, and if the limit as n goes to infinity of the absolute value of the terms of the sequence is 0, okay, then this will mean that the limit as n goes to infinity of an is 0. Okay, this is specific to 0. This wouldn't be true if the limit of the absolute value was 1 or something. This is specifically saying if the limit as n goes to infinity of the absolute value of the terms is 0, then we know the limit of the original terms here as n goes to infinity will also be 0. Okay, so we're going to look at several examples where we can make use of these different results. So let's look at our first example here. Again, in each one of these, we're trying to determine if the sequence converges or diverges. So we have an is equal to tangent of 2n pi over 1 plus 8n. So notice this is a situation where I have a composition of functions. I have this inside function here, and then I have tangent of that. Okay, so we're going to be making use of that result that talks about when I can pull the limit inside. So I have the limit as n goes to infinity of tangent of 2n pi over 1 plus 8n that we're trying to compute. Okay, and so as long as the limit as n goes to infinity of what's inside is something where tangent is defined, okay, we can proceed this way. So we can say that this is tangent of the limit as n goes to infinity of 2n pi over 1 plus 8n. Okay, notice with what I have inside here, I have the highest power in the numerator here being n, and the highest power in the denominator also being n. So we can say that that limit's going to be the coefficients of that n power in the numerator divided by the coefficient of the n power in the denominator. So I have 2 pi over 8. Okay, just as another little aside, if you'd done this the longhand way, 2n pi over 1 plus 8n, if I divided the numerator and the denominator by n, I'd have 2 pi over 1 over n plus 8 where 1 over n goes to 0. So that is 2 pi over 8. Okay. Notice that this is tangent of pi fourths, and tangent is defined at pi fourths, so we're good with the steps that we've taken here. Tangent of pi fourths is equal to 1. Okay. So we can say that our sequence, in this case, and here I'll write the full sequence, tangent of 2n pi over 1 plus 8n converges to 1. Okay, remember, anytime we're starting a question about sequence convergence, we're going to be looking at the limit of the nth term. Okay, so here's another example. I have an is equal to cosine squared n over 2 to the n. And I know I'm going to have to find the limit as n goes to infinity of cosine squared n over 2 to the n. Okay, so what is it that tells me that I might have to use one of my theorems that we mentioned before? Well, the limit as n goes to infinity of just this numerator here, cosine squared n, that's actually something that doesn't exist. Okay, because cosine squared n is going to be something that oscillates. Okay, so I can't just find this by doing the limit of the numerator or the limit of the denominator. But we do have some really nice properties of our cosine function that show it's always bounded between some values. So the squeeze theorem is going to be helpful in this example. Okay, so some cases where the squeeze theorem will be helpful. Okay, often comes up when you have things that have sine or cosine in them, or arctangent. So these are not exclusively the only times you'd use the squeeze theorem, but just keep in mind that we have the following facts that can be helpful. Cosine x is between -1 and 1. Okay, we oscillate between -1 and 1 with our cosine function. With sine also stays between -1 and 1. And your arctangent function, you'll also see come up in some examples. Arctangent is between -pi/2 and pi/2. Okay. The only one we're going to need in this example is some information about cosine, but I just want to mention these inequalities might be useful in some other problems that you'll see. Notice that I actually have cosine squared here, so I can say that cosine squared, well, that won't be negative. That'll be bigger than 0 and less than or equal to 1. Okay, so that gives me a bound to start out with my squeeze theorem. And if I divide each of these terms by 2 to the n, that keeps my inequalities in the same direction. Okay, and now I have my given sequence here. This is like the Bn in the squeeze theorem statement, is between this an of 0 and this cn of 1 over 2 to the n. We see that the limit as n goes to infinity of 0 is clearly 0. And the limit as n goes to infinity of 1 over 2 to the n is also 0. So that forces this function that's between those two, this sequence, the limit as n goes to infinity of cosine squared n over 2 to the n to also be 0 by our squeeze theorem. Okay, so we can say that our sequence here, cosine squared n over 2 to the n, converges to 0. Okay. So you want to keep the squeeze theorem in mind as something that can be helpful in some examples. Here's just a couple more for us to look at. Here I've got an is equal to -1 to the n all over 2 root n. Notice that this is something that's going to have alternating signs. It'll sometimes be -1 over something, it'll sometimes be +1 over something. So it'll be useful to try to use our result that we had before that said if the limit as n goes to infinity of the absolute value of an is 0, then the limit as n goes to infinity of an is 0. Okay. Notice that the absolute value of an here would be +1 over 2 root n. Okay, and the limit as n goes to infinity of 1 over 2 root n is clearly 0. Okay, so this tells us from this theorem that the limit as n goes to infinity of -1 to the n over 2 root n is also 0. Okay, so we have that our sequence here of -1 to the n over 2 root n converges to 0. Okay, so we've seen a couple of examples that converge to 0. Of course, there's other numbers they might converge to. We just happen to get 0 in a couple of these. Let's just look at 2 more. So looking at this example 4 here, I have a sequence that goes 0, 1, 0, 0, 1, 0, 0, 0, 1. So I'm getting increasing number of zeros here, but I'm always coming back to a 1. So when you just think about the idea of whether this is going to converge or diverge, even though I am getting longer and longer strings of zeros, it's always going to pop back to a 1. So this is doing some kind of oscillating. So this sequence diverges. It's not getting closer and closer to just one particular value. It's still jumping around. Even though it's going to spend more and more time kind of at 0, it's always going to be going back to 1. So that's a case of a divergent sequence. So here's our last example. I have an is equal to n squared over e to the n. Okay, I know to determine whether this converges or diverges, I'm going to have to deal with the limit as n goes to infinity of n squared over e to the n. So this is going to use a new technique that we haven't seen so far. Notice I can't simplify this just by dividing by powers of n, and it's not a composition of functions, and it's not something with negative numbers in it. But if I tried to take this limit, I would get some kind of infinity over infinity, which is an indeterminate form. So we want to try to use L'Hopital's rule here, but remember our n's that we have when we're dealing with sequences are just integer valued. And if I want to use L'Hopital's rule, that involves taking a derivative, so I need to be working with a function. Okay, so we want to use L'Hopital's rule, but first define a function. Just so we're clear on what our variables are actually representing. Okay, since n is just integer valued. Okay, so we'll let f of x be x squared over e to the x, with the understanding that x is now taking on all values that would be in the domain of this function instead of just the integer values. And so now we can look at the limit as x goes to infinity of x squared over e to the x. We know that that's infinity over infinity, so we're going to apply L'Hopital's rule to this. So that means I'm going to have the limit as x goes to infinity of the derivative of x squared over the derivative of e to the x. So we notice that we get infinity over infinity again. So we're going to be able to apply L'Hopital's rule a second time. So I'm going to have my limit as x goes to infinity of 2 over e to the x, which we see comes out to 0. Okay. So remember our original definition of sequence convergence said that if the limit of the function went to 0 and our sequence was just equal to our function at n values here, at our integer values, then the limit as n goes to infinity of this version here with n squared over e to the n, that'll be equal to the same thing. So we know that this is now 0. Okay, so our sequence of n squared over e to the n converges to 0. Okay, so this gives you an idea of how we're going to apply sequence convergence in various examples. Please let me know if you have any questions.